Have you ever watched your brother knitting machines when it's working in pattern and wondered how exactly does it know where to put the needles for the next row? That's what we're going to cover here. I'm using a 930 here, electronic, but the principles I'll be describing are exactly the same for the entire range of both the electronic and the punch card machines. I'll mention some differences for the punch card machines down at the end. First, a little teaser of part of the mechanism that happens deep inside the bed of the machine. If you're going, what are we looking at here? Stay with me and I'll explain. We'll look at this in more detail later. The pattern I was knitting in the intro there is this one, pattern number 31 from the Stitch World book, which describes the built-in patterns in these machines. And of course, as with all these patterns, it's binary, white squares and black squares. White squares will go to B position and black squares to D. If you have a 910 or a 950, you'll be using these optically read cards known as mylars, but again, of course, black and white squares. Or if you have a punch card machine, it's either a hole or a blank, a hole or not a hole. If you've been using these machines for a while, you get to recognize the needle sequences as they happen. In this case, see the areas of 1 by 1 and solid red and solid white. As we're doing two color ferrule knitting here, the back row B position needles are picking up the white yarn, and the front ones, the D position, are picking up the red. Needle positions are labelled here on the ends of the bed. B and D are the ones we're interested in for the needle patterning. B and D. When you're knitting a row in patterning, the front half of the carriage, the left half in this case, the mechanics underneath there are knitting the current row as presented. The two rows of needles go in underneath into two parallel paths to pick up the two yarns. Then it's the second half of the carriage, the trailing half, that is doing the interesting bit, which is selecting the needles for the next row. And coming the other direction, again the leading half, in this case the right, is knitting the current row. And the needles appear out the trailing side in their two lines ready for the next row. And a quick reminder of what the needles look like. This is the business end here that does the actual knitting with the latch. This part in the middle is the butt that the carriage uses to move the needles around. And this tail at the back has a role to play in the needle selection, so we'll mention that again when we get there. One of the reasons why this is all a bit of a mystery is that the mechanical parts where most of the magic happens are hidden inside the bed of the machine. In this exploded diagram from the service manual, you'll find that the bed, the sponge bar and the gate pegs assembly will be familiar, but you may not be so aware of the needle retaining spring in the middle, nor the needle selection plates down at the bottom. Let's look at the needle retaining spring first. It's kind of a comb shape. This view shows the machine out of its case and upside down. The comb spring, aka needle retaining spring, is right there in the middle. Or looking straight in from the left-hand end like a cross-section view. The needle retaining spring is installed at an angle with its long end attached low down there in the front. And then each individual prong sits under one needle. The very end prong just sits up against the bed, but it's the second one that's interesting here. What we're looking at is the prong that's sitting under needle 100. And looking up from underneath again, that's the extra one on the end that doesn't do anything. And this is an individual prong on the end needle. And you can actually see the spring from on top. If you take out a few needles, you can see it there. Now let's take a look at the needle selection plates shown at the bottom of the diagram. Also notice the three little rods labelled 41 down there in the lower right. Orient ourselves as to where the needle selection plate assembly sits. We're looking in again at the left-hand end, and these little springs are the very left-hand end of the needle selector plate assembly. I happen to have a spare of this particular assembly, so I can show it to you out of the machine. It sits directly below here. There are 8 of these little springs on the ends, one for each of the 8 needle selection plates, which themselves are a long strip of thin metal with little hooks on top. When I turn it sideways like this, you can see that between all the 8 plates there are 200 of these little hooks, spaced 4.5 millimeters apart, and one for each needle position. With this piece of paper in here, we can get a better view of just one of the plates. They have hooks. The hooks are spaced 8 needle positions apart. And they can move just by this tiny amount and pulled back by the spring. Only one of them has any effect at any given time. There's a hook lined up beside the tail of each needle, and if the hook has been pushed down by the carriage, the sliding motion of the needle plate causes the hook to engage with the needle. Let's take a look at how this sideways motion is initiated. Let's move down to the right-hand end of this assembly, where there's a section that interacts with the information coming from the card or the solenoids. My spare assembly happens to come from a punch card machine, so there are 24 of these little slots. On the electronic there are 16 slots spaced a little further apart, but the way they work is exactly the same. Remember the little rods that I pointed out in the diagram, labeled 41? There's a whole set of those, and one goes through each of these holes and is able to move just one of the plates. And the reason it's able to move just one is because inside this area of the plates there are some slotted and round holes. If we look at the upper row here, the row closest to us, you may be able to see that there's a round hole every 8th needle position, and all the rest are slotted. So if we use this round hole here, our top plate moves. If I go into any of the others, I'll be moving a different one further down. There, and if I go back to this next round hole, again I'm moving the top plate closest to us. Now we're going to take a look at the camshaft assembly, which we can see without taking the machine completely apart. Just open up this area. Though if you have a 910, you'll have to remove the Mylar reader assembly to get in here. I'm sure you're all familiar with this belt, which is how the carriage and the mechanics inside the bed connect with each other and keep their timing in line. Here we have a set of 16 cams that rotate on a shaft and 16 solenoids behind them with a little armature sticking out towards us. The solenoids are under that metal strip in the back. Ignore the little red arrow there. That's from when I first got this machine and it was mispatterning every 16th column. I was convinced it had a dead solenoid, but in fact I ended up changing out the electronics board and it all leapt back to life. The solenoids themselves seem to be very reliable. This is with no power to the machine. Now we've got just a few needles in work over here on the right hand side. And now they've all been brought forward to D position. We're in KC mode here with no power. So what's happening is kind of a cart driving the horse. The main thing that the cams are doing is causing some sideways motion below them, which I'll show you in just a moment. But I believe it's kind of incidental that this is also causing the armatures to flip up and down as they follow the eccentric shaping of the cams. Okay, so now I have the power on, and the pattern that's selected is still the same one from earlier with this sections of 1 by 1, which you can sort of see here. We'll get some clearer examples later. In this view, I want you to focus your attention on the little vertical rods under each of the cams. Watch the way they move from side to side. Again, we have no power, so they're all moving. It's this sideways motion that pushes the little rods that go through underneath to the needle selection plates. So this little armature is sticking out from solenoid, is controlled by it, and underneath it is a little lever. This little lever is kind of a U-shaped wire. It goes down underneath and up again under the cam. I hope you can see that the other end is in fact moving up and down too as I push on the armature. And it's just a weird camera angle. They are in fact in a straight line. In this diagram, the part of the armature that we can see is marked in red, and the U-shaped rotary cam lever is marked in blue. If you've taken the machine out of its case, you can look in from the back and see the actual solenoids. Here's the left-hand end one, and the little orange dot is the wire coming in to feed the coil. Or from the other end, we can get maybe an even better view, solenoid up there in the top right, and the rotary cam lever. This is that same U-shaped lever that I mentioned earlier, the longer end under the armature and the shorter end under the cams. I didn't take my electronic machine completely apart to show the underneath of this part of the mechanism, but here are some shots from when I took a punch card machine apart, showing where the little rods go and how they connect. One end just sits between the needle selection levers, and the other end goes through the needle selection plates. And just to labour the point, once it's all assembled, the sideways motion of one of these U-shaped levers causes a needle selection plate to move sideways. So I have a pattern programmed in now that is 2 rows of all white and 1 row of 1 by 1 black and white. On an all white row, all the solenoids are engaged, all the armatures are down solid, which means that all the levers are clear of the cams. The cams continue to spin any time that the carriage is moving, but when it's being fed a white square, or in this case a series of white squares, the armature will stay down, the lever will stay clear of the cams, and no side-to-side action happens. Whereas for the 1 by 1 row, you can see the armatures flapping up and down for the black squares and solidly down for the white. Each solenoid is reused every 16th needle across the bed. Even at the fastest speed you could possibly move the carriage, the time between needle 1 and needle 17 is plenty for the electronics to have fed new information to the solenoid. This is how an electronics machine's needles are individually addressable all the way across the bed. For us to be able to see what's going on here, I intentionally chose repeating patterns so that needle 1 and needle 17 are both doing the same thing. And this is a slow-mo shot exactly as it came off my iPhone, complete with slowed down sound. Everything we've seen so far is basically set up for the critical role that the carriage plays in all of this. There's a lot of mechanical complexity under here, most of which is for knitting the various different kinds of stitch patterns. For our purposes, I'm going to draw your attention to these pieces here, this curved piece, which is where the needle selection happens. Each needle in turn is pushed down by this curve. And of course there's another one on the other side for when you're going in the opposite direction. You can watch this flap change position as you move the KC knob from NL to KC. This changes the outgoing path of the needles. Think of the needles as travelling left to right in this shot. They've done their knitting of the current row off camera to the left, and then whether patterning or not, they all gather here and make their way out. In this case we're in non-patterning mode, so they all go down to the bottom and out to B. Now we've changed to KC mode and the flap has changed position so that all the needles are directed towards our curved piece. For a needle represented by a white square that does not have any hook action going on underneath, the needle is held straight by its spring. It marches down this hill and back up the other side, pushes past this little gate and out to B. For a needle position represented by a black square, and so the needle does have one of those little hooks pushing on the tail of the needle underneath, it marches down this hill in the same way. And what seems to happen is that the hook causes it to stay in the down position for a tiny distance longer, which in turn causes it to hop over this little partial wall and out to D position. And the lace carriage pre-selects in the same way that the K carriage does. Here's its same curved piece, and the black squares with the hook action going on underneath get directed up here and out to D, and the white squares out here to B. So remember the teaser from near the beginning? I hope it makes a bit more sense now. We're looking in from the back of the machine at what happens when the carriage passes over and that little curved piece pushes down on the needles so they interact with the hooks below. An important thing to notice is that even though the hooks are wiggling around like crazy, most of the time they're below the level of the needles and not interacting with them. It's only when a needle gets pushed down that little curved piece that the hook has any effect. You're looking for this dip happening in a sort of wave motion as the carriage goes across. By the way, a dead sponge bar will cause this whole thing to not work. If you want to take a look at these hooks yourself without taking the machine completely out of the case, you can actually access it with a mirror in either here or down to the left under the toolbox. Just be sure that the mirror you use is plastic or glass and does not have a metal edge or backing, in case you might short something. This is an alternating black and white row. This row is all white. This one is all black. That's basically it. We've covered all the ground from where the patterning either calls a solenoid for a white square or doesn't for a black square. It's entirely mechanical from there through the cams, the U-shaped levers, the rods which move the needle selection plates and therefore the hooks. And then the carriage directs all the needles downwards and only the hooked ones get deflected sideways. Let's talk a bit about punch cards. The punch card mechanism, of course, was designed first, came on the market around 1970, and then the electronic version grew out of it about 1980. What we're looking at here is the camshaft from a punch card machine. It's got 24 lugs for the 24 holes on a punch card, and it gets to each of them once in one rotation. With a punch card, each column on the card always controls a fixed set of needles. So the rightmost column, for example, it feeds to needles right 12, right 36, 60, etc., and similarly on the left. As the camshaft rotates every 24 needle widths, it gets fed the same information again for needle 25 as for needle 1. This clip from my previous project, the long end of the U-shaped levers sits directly under the card and either slips through the hole to remain in its up position or gets pushed down by a blank, the absence of a hole. We're looking at a card here that has sets of 3 holes and 1 blank. Just like with the electronic, directly under the camshaft there's that row of the short ends of the U-shaped levers. And any place where there's a hole in the card, they're doing that same side-to-side motion. And if there's a blank in the card, the long end of the U-shaped lever is forced down, so the short end also forced down, putting it below the level of the cams. So the cam rotates above it and has no effect. Then from here on out, it's exactly the same as we already discussed. That's the end. Thanks for watching. There's a couple more minutes tagged on the end here, which is 2 more slow-mo videos just for fun. They don't add any new information. Actually, I lied. I did learn one new piece of information from watching these slow-mo videos, and that is about the noise that these machines make. When the needles return from having been pushed down, especially the ones that have been held by the hooks, they make a noticeable noise as they slam back up again.